Hello! So, today we're going to look at the conservation of energy. So this is a really important aspect of energy that we need to learn. Not every single energy question comes down to this, but a lot of it does, and it's really important when we're looking at how do things work, right? If I want to know how things work, this is a really good tool that we can use to kind of analyze what's happening. So let's first of all talk about mechanical energy. The abbreviation for mechanical energy is just ME, okay? And so this is basically just the sum of all energies we can calculate. Okay? So this won't include things like nuclear energy or heat energy, but it includes KE, PE, G, I'll go ahead and put plus here, plus PES, so spring potential energy. So every single thing that we know how to calculate is part of the mechanical energy. So that's kind of what we spent the previous few note sections talking about, and now we're kind of putting it all together. Okay, so ME just equals this. Okay, it's just the sum of KE plus PEG plus PES. Okay. Now, non-mechanical energy, like I said earlier, this would be things like heat, nuclear, chemical, okay, and other things as well. So there would be some things that are not included. But those are the things that we don't know how to calculate and we basically just ignore, okay? So conservation of mechanical energy, you'll often see it written as something like MEI equals MEF. Okay? So the initial mechanical energy is equal to the final mechanical energy. So that's a frequent way that you'll see people write it. I'll also often just write it as EI equals EF, just saying that initial energy we have is equal to the final energy we have. And for AP, oftentimes just writing this can end up being a point. So it's really important that if you're doing an energy conservation question, you're really starting with that. So you're showing me or another person who's grading your work that you know that this is a conservation of energy question. Okay? So now that we kind of have this basic idea, let's actually look at what does this look like? How do we actually do this, right? This is our basic setup, but how do we actually solve a problem? 1 second, let me erase. Okay, so we have example number 9. Starting from rest, a child goes down a frictionless slide from an initial height of 3 meters. What is her speed at the bottom of the slide? So I start with EI equals EF. Now, what I need to do for both the beginning and the end is write the types of energies I have in this scenario. Okay? So at the beginning, she is starting from rest, and she's going down this slide with an initial height. Okay? So if she's starting from rest, does she have kinetic energy? No. No kinetic energy. Is there any springs involved in this problem? No springs involved, so we don't need to worry about PES. Okay? We only have what kind of energy? PEG, right? My gravitational potential. So I'm starting with just PEG. Okay? Now, because this is staying on the left-hand side, there's sort of just an implied I here. Everything here is my initial, okay? Which means even if I have a PEG over here, those are not the same. Okay, so one is standing for my initial, and everything on the right side is standing for my final. Okay, so even though I'm writing sometimes the same variables every time, sometimes these variables are different on the different sides here, right? This is going to be different from here. Now, at the end, she's at the bottom of the slide, so she's at her lowest point. So does she have any potential energy left? No. So she's not going to have potential energy, but is she moving? Yes, she is moving, so I will have KE at the end here. Okay, so my first step is just writing down EI equals EF. My second step is going ahead and applying what types of energies do I start with, what types of energies do I end with. Okay? Then my third step is plugging in what these formulas are. So I have mgh, right? That's my formula for PEG. And I have 1/2 mv squared. Okay? So we can go ahead and write down these steps. So step 1, EI equals EF. Step 2, types of energy at start/finish. And step 3, plug in formula. Okay, so you have to go ahead and plug in that formula. So you can, let me say it this way. I do not want you to go ahead and start writing numbers yet. I want you to write this out. Okay. The way, especially AP is graded, if you make a mistake with plugging in numbers, you can often miss that point. If I write this out first, I can prove that I know what's happening. So this is an important step to write out. Okay, next I can go ahead and start plugging in numbers. Okay? But you'll notice this mass and this mass are the same. It's in every single term, so I can go ahead and cancel that out. Okay? If I divide everything by m, those two m's cancel out. So at this point, I now have g, which I'm going to just round to 10. So I have 10 times h, which is 3, equals 1/2 times v squared. Okay? And so now it's pretty simple. So I'm going to multiply by 2 to cancel out the 1/2. So I'll have 2 times 10 times 30 equals v squared. So I have 60 equals v squared. So v is going to equal the square root of 60. Okay? Which should be about 7.8 meters per second. Okay? You might need a calculator to check that exactly but it should be about that number. Okay? So remember, our first step, EI equals EF. Okay? If you wrote MEI for mechanical energy and MEF, that's no problem with that. Okay? Remember, then we need to plug in the types of energy we have. What types of energy are we starting with? What types of energy are we ending with? Okay? Then finally, or next, we're going to plug in the equation for each. What's my equation for my PEG? What's my equation for my KE? So every time you see KE, you're writing 1/2 mv squared. Okay? Then finally, you can plug in numbers and then go ahead and solve. If you have no springs, mass will cancel out. Okay? So if there's no springs involved, m will be in every single term, and you can go ahead and cancel that out. Okay, let's look at the second example. A pole vaulter runs with a speed of 11.7 meters per second. She vaults over the bar with a speed of 1.18 meters per second. How high is she off the ground when she's going over the bar? And they give us a mass. Okay? So, first step, EI equals EF. Okay? We want to say that we are using conservation of energy. We know that the energy at the beginning is equal to the energy at the end, because energy can't change. Okay? So, next, types of energy she starts with. So she's running on the ground, right? Which this is actually a very fast speed. So it's very impressive that she's running this fast. So what type of energy is that of that motion? KE, right? So go ahead, you got KE. Now if she's on the ground, does she have potential energy? No potential energy. Okay? Now, we are going to look at when she is going over the bar. Okay? At this point, is that pole bent? No, it shouldn't be bent when she's at the very top of her peak, right? And so even though there is a spring energy involved here, because that pole gets bent, that's kind of like a spring potential energy, it's not at the very beginning and it's not at the very end, so I don't actually have to worry about it at all. I'm only looking at this point here where she's running and the point where she's now going over the bar. Okay? So when she's going over the bar, is she above the ground? Yes, she is above the ground. And also, is she moving? Yes. So that should give me two types of energies. What types of energies are those? Hopefully you said PEG, or gravitational potential energy, and KE. Now, this is what I was talking about earlier. This KE and this KE are not the same. These will be different numbers, right? So this is sort of my KEI, and this is my KEF. Now you don't need to write KEI and KEF every single time. You just need to mentally know that these are different things. Okay? So let's go ahead and do my second step, or third step. Go ahead and plug in my formulas. So I have 1/2 mv squared, that's my VI, right? mgh plus 1/2 mvf squared, right? So these are different values, okay? Now, let's go ahead and think about this. I have m in every single term, so what can I do? Yes, I can cancel out my m. Now, I have 1/2. My initial velocity is 11.7. I'll square that equals g, which I'm going to round to 10, times h, which is what I'm looking for, plus 1/2 1.18 squared. Okay, I'm going to go ahead and move that to the other side. So I have 1/2 11.7 squared minus 1/2 1.18 squared. And then this equals 10h. Okay, so I just need to divide this side by 10. Okay, so h equals that. So we go ahead and grab a calculator. Okay, and let's go ahead and find out what this gives us. Okay, so I got 68.3 meters. That seems a little high, okay? I will say this is unreasonably fast. And I will also say that some of this energy will be lost, right? It's not going to be a perfect conversion because some of our energy is going to get lost to friction. So this is the sort of, if you're running really, really fast and you have this ideal situation where you don't lose any energy, what could happen? Okay? So, one last part and thing to think about is when is mechanical energy not conserved, right? Or total energy. Well, in the situation above, we kind of already talked about this, right? Mechanical energy is not conserved when there is friction slash heat slash chemical, right? Or any other type of other energy. Okay? If there's any other type of energy involved besides kinetic energy, gravitational potential energy, spring potential energy, then mechanical energy will not be conserved. Now, total energy is always conserved. Okay, so total energy is always conserved, but mechanical energy, which is what we calculate with, what we use, won't be conserved if we have some of these other types involved. Now, even with friction, we can actually do a calculation with it because we can find the work done by friction. Okay, so in some ways, we can actually find out maybe how much energy went to heat by using the work done by friction. So just a simple work equals F times D, right? And that will kind of help us avoid the problem that we can't directly calculate heat. Okay? As always, if you have questions or concerns, send me an email. There we have lots of good practice questions here. So go ahead and work on those.